I'll figure that out later. All right, so here's what we've been doing. We spent a bit of time on traditional optics, classical optics, lenses, mirrors, things like that. We took a detour because we wanted to explore wave behavior. And in particular, we wanted to explore superposition. And part of the reason we did that is because the next couple of chapters are devoted to superposition of light waves to produce interference patterns. And so that's sort of the reason we took that detour. There are other reasons too, as you'll see later. But the focus here is on the concept of interference. And so today particularly, we're actually covering all of chapter 35 today, I believe it is. All of it today. So, all right, so you're familiar with these concepts here. We've talked about them before. What interference means. Interference means that superposition applies to things like waves. And when you have two or more waves at a particular point, that there will be a net result of those waves. You add up what their displacements are, and it's as if there is a single, maybe complicated, but they're as if there's a single wave acting at that particular location. That's nice. So what we're going to do here is we're going to look a little bit about propagation of waves. We're going to focus on our wavefront perspective here. And we are going to consider when waves are interacting. So this figure that you see here represent wavefronts. And the way that you can interpret this is each of the circles that are given here would represent, say, the maximum amplitude, or what we call the crest of the wave. So, there are waves throughout the space here, but the wavefront will be illustrated by mapping out where the peaks are on these waves. So that's what we're looking at here. Give me 1 second. Okay. So we have a source. Source 1 produces a bunch of wavefronts of a given wavelength, lambda. They travel at a speed that is determined by the frequency times the wavelength of the source. Why is my mouse down? Oh, now it works. All right, here we have two different sources. And the idea that these are effectively equivalent waves. So just imagine it could be sound, it could be light, but we're imagining that they are identical. They're produced in a single wavelength. We'll assume they have the same amplitudes, speed, all of that stuff. And the sources are going to be in phase. So they're identical pretty much in every way. And as you can see here, we have wavefronts that are over. And when you look at, say, point A on the left-hand side here, point A happens to be a point that is equal distant from source 1 and source 2. So we know, because everything is the same, especially that they're in phase, that at location A, we are going to have the exact same wave present there. And we've selected A to be a point where the crest exists. So that would be what we refer to as complete constructive interference at that location there. Okay. Now at point B, let's go back a little bit. Point B, well, when we map out the wavefronts, we can see that point B looks a lot like point A, in the sense that point B, that we have crests of these two different wavefronts coinciding right there. But you will notice that it's not the same distance from the two sources. The source located at on the negative y-axis, what we call an S2 here, is a bit of a farther distance. But still, the waves are constructively interfering here. And the reason why that's occurring is because even though the path lengths are not the same, the difference in the path lengths come out to a whole number of wavelengths. And because of that, there's still a constructive interference. So we're looking at those two paths there. And if it just so happens that there are 7 wavelengths from S1 to point P, there is some other multiple wavelengths going from S2 to B because, again, the crests coincide. And if it happens to be 9 lambda here, the path length difference is 2 lambda. As long as that is a multiple of lambda, we're still going to have constructive interference. So you don't necessarily have to have the exact same distance. You need to have the same, well, you need to have multiples of your wavelength so that the crests line up. That's the idea. Okay, now let's go back to point C here. Now you see what's going on with point C. Point C is at some kind of intermediate point. It's kind of almost in the middle of the crests that come from source 2. And it's a little bit past one of the crests for source 1. And if we happen to work out the path length differences for these, let's say, well, S1 is more distant, say it's at 9.75, and S2 is at 7.25. Taking the difference of those produces not a integer multiple, but a half integer multiple. And you know, when you line up, and what that's going to mean is you're going to be lining up regions of the waves where you don't have constructive interference. And so this would be an example of destructive interference. And it purely comes from the fact that you're dealing with these half integers. And half integers are going to be basically in between the two crests. What's in between the two crests? All right, in between the two crests is a minimum there. So that's going to be a destructive interference. Okay. Now notice that individually the waves are not being presented at their, minimums here. That's not what's happening, but the combination of the two produces the half integer thing. So, all right. So we have a very interesting pattern that we can do here. We have the same picture, but now we have mapped out. So here's a really interesting activity to do, which, our next lab is going to be on this topic here. It's going to be on interference. And honestly, I don't even know what the activities are going to be yet. I haven't looked into the Phys set. I usually do that in the weekend. But this is a really neat activity. What you can do is you can take this figure here and you can map out different constructive interference locations. Different modes, basically, is what we're talking about here. So if you look at the m equals 0 mode, what that means is this. Everywhere along the x-axis, the distance between the two waves are the same. All the locations where there is constructive interference, it's because the path lengths are completely identical. What's happening with the m equals 1 line is we are identifying all the locations where there's exactly a 1 wavelength difference between the paths. And that's still going to result in constructive interference. M equals 2 is when there's a 2 wavelength path difference. 3 is a 3 wavelength path difference. And you can go on from there. And it produces this really interesting pattern where we connect all those points and we generate these lines. And these are called nodal and antinodal curves. Constructive interference is the antinodes. Remember, that's the maximums. And the nodes are where we have destructive interference. And so what we're showing here are the antinode curves. In between, we would have our nodal curves. Now, that's not illustrated here, but you can create a picture like that. And so we have this sort of map. And we have locations all throughout the space here where you would expect to see these things. Now imagine this was sound, right? If you stand on any of the antinodal curves, you're going to hear a much higher intensity of sound than you normally would. Whereas if you stand on the nodal curves, you're going to get a destructive interference. And depending on the situation, that could actually result in not hearing any sound at all. I mean, obviously there's other factors involved. Like wave, sound bounces off things. It won't be perfect, but this is actually really interesting, and this applies to any wave, right? It's any sound, light, whatever. In fact, the illustration in the picture here shows ripples on water. If you were to drop two objects into water in the precise same way, we can actually visually see on the surface of the water, the patterns of these things. And so this picture here is a really beautiful illustration of that phenomenon we were talking about here. Okay, now we want to apply this principle to light. Okay, you can do it for any kind of waves, but we're technically still on the topic of optics, and we're going to continue on that. But we're now delving in to more modern principles now. And this experiment here was an extremely important experiment, arguably ushered in sort of the notions of modern physics. And we call this the double slit experiment, or sometimes referred to as the Young interference experiment. It's performed by an individual by the name of Thomas Young. And so the idea is this. Here's how this works. If you were to take light of a single wavelength, right? Monochromatic light. Pick a wavelength, doesn't matter what it is. It's got to be monochromatic, though. There's a reason for that. Talk about that a little bit later. And what happens is we have that light incident upon a large screen, and the screen has a very narrow slit in it, right? And what that does, according to Huygens' principle, is when light exits that slit, it's going to diverge away from that. We're going to call that S1, diverge away from the source. And remember, that's what Huygens' principle is all about, is that a given wavefront, every point on the wavefront is a new source of what we call wavelets. And so it's like this, what would be the right word for that? I don't know. But, the light, if it's coming straight, it won't continue straight. As it exits out the thing there, we're going to see that pattern, that Huygens principle pattern, where the light's going to continue to diverge away. That's the nature of that light. So now we have light coming out from the slit here, and it's diverging away. And then now that light becomes incident upon more slits. Upon two more slits. We'll call those S1 and S2. When that occurs, the light that comes out of those slits will produce a pattern on a screen where we see different bands of light. We don't just see light shining on the screen, we see a pattern of light. I gotta get my mute button in here. All right. So, and what's occurring here is the idea that, light is a wave. And if there are path length differences in the light, then you certainly can have constructive and destructive interference. The joys of teaching in your home with children.
The background is pretty fitting.
Yes, really. This is pandemic life, people. Everything is fine. This is fine. All right.
Everything is not fine.
Yes, this is fine. Do you see my background, buddy? It's the "this is fine" meme. All right, get out of here with that cat. All right, sorry. All right, so it's a simple experiment to do. I mean, you produce screens of narrow slits. Oh, hold on. Rebecca, I need some help. Everybody's kind of being loud right now. Okay, thanks. Oh, I wasn't muted. Ha! Shut up, mute. All right, whatever. All right. So yeah, it's a simple experiment to do. Hold on. Everything fine with the dogs, the cats, pets, whatever?
Apparently, I guess the last time the door was open, she got out.
Okay.
So she couldn't.
All right. Anyway, so we're going to explore this behavior here. We interpret the bands that are seen here as interference patterns. Depending on the path length that the light has to travel, there's going to be various constructive and destructive interference things. So this is a very important experiment because this really establishes the wave-like nature of light. Light wouldn't do this if it didn't behave as a wave, meaning it wouldn't happen if light didn't have the ability to constructively and destructively interfere with itself, basically. Okay. So let's keep going here. All right. So, but I have a similar picture listed here on the double slit experiment. And what's happening here is we have our plane waves to start off with. So let's say we've established those plane waves. You know, just put it that way. And they exit out of these two slits here. And we draw the wavefronts. And so you can see, and I have the lines here, similar to the lines that we have drawn in the previous example. M equals 0, M equals 1, M equals 2. These are called orders, and they refer to multiple wavelengths of interference. So the M equals 0 is where the path lengths between the two slits and the location of interest are identical. M equals 1 on top and bottom is exactly a 1 wavelength path difference, and so on and so on. Okay, and we get a pattern that is seen here. And most intense in the middle, diminishes as you get farther away. There's various reasons for that. It's not necessarily due to the fact that the light is, diminishing with distance, because that's not a big factor, but it really has to do with, how many, how the interference is occurring, basically, put it that way. All right, so let's look at the geometry of this stuff and try to actually put some numbers behind this. All right, so imagine that we have our double slit here. Now, the idea typically is that, wavelengths are small, right? I mean, we're talking about, if it's visible light, we're dealing with things that are hundreds of nanometers, right? Red light sits at around 700, it's 650, but the human vision goes from about 400 to 700 nanometers. So we're dealing with hundreds of nanometers, right? So if we're talking about path length differences, I mean, they got to be pretty darn small. So the separation between the slits is actually extremely small, millimeter or less, honestly. The distance to the screen's got to be pretty big, so we really can see those patterns there. So something like the distance to the screen and maybe like, you know, 3 orders of magnitude larger. And it needs to be larger in order to produce this kind of effect here. All right, so we have our double slit here. This is a macro view. And we have our light coming over here. And there is an angle that we can define, which is the angle from the path of the light to a line that is perpendicular to the screens here. Okay, so we have this big length L that represents the distance to the screen. We have our lambda here. And so what that means is if we look at different locations on the screen, it can be indicated with a tangent function. Nice tangent. Okay. Now, let's zoom in on that double slit there. Our slit spacing we're going to call D, okay? And so what happens is we have a path of light coming out the top here. And it moves along that angle that we have specified, and it hits the screen there. Now, traveling down a bit to the slit spacing, you can see we can make a triangle here, where the hypotenuse of the triangle is the slit spacing. The longer leg of the triangle represents a perpendicular distance between the 2 paths. And then right down the bottom here, okay, and I'm going to highlight this with a similar color, this little distance right here. Oh, you can't see that too well. Let's make that super thick. Right there. That is the juicy stuff. That is the path length difference. That's the stuff we care about for interference. And that path length difference, according to this triangle here, is given by d sine theta. Okay, it's the same theta that's existed here. The triangle that we have here is a similar triangle to the one that's in here. Again, the hypotenuse is d, and the side opposite is delta r. So delta r represents our path length difference. And guess what? You're going to have, we call them fringes, by the way, fringes, where the constructive interference is taking place. We are going to see fringes at angles that correspond to these path length differences. Delta r are going to be multiples of lambda. That's what we need for constructive interference, multiples of lambda. So we can replace delta r with m times lambda, where m are the different orders, right? That corresponds to a 1 wavelength difference, a 2 wavelength difference, a 3 wavelength difference, right? And so we equate these two, and now we have a relationship between an angle, right, and the wavelength of the light that's being used. And this angle here is exactly where we expect to see the fringes, okay, because it's all based on this path length difference. This is pretty nice stuff, pretty awesome. All right, let's put it together here. The bright fringes on the screen are going to be indicated by d sine theta m lambda. Remember, d is the distance between the slit. Sine theta is part of that triangle there. D sine theta is the path length difference, which if it is equal to integer multiples of your wavelength, you got constructive interference, you have bright fringes. To make destructive interference, the path lengths need to be a half integer multiple, right? And so the way we're going to illustrate that is simply by adding a 1/2 for our order here, right? So if m equals 0, in the top here, we get a fringe right in the middle, exactly in between the 2 slits. Boom, we got our fringe there. Now, for a 0 down here, this is going to correspond to a half wavelength. We're going to get destructive interference there, and you'll see 2 dark bands over there. Then we go to m equals 1 up here. That's the first set of bright fringes. Then we have are dark fringes, and so on and so on. Okay. So simple, so elegant. It's actually pretty surprising, to be honest, that it took so long. I believe the double slit experiment, now I'm going to go with 1860 here. That's my recollection. Let's just double check this. Double slit experiment. What year was that? I thought it's 1860, but... Oh my gosh, I am so wrong about that. That is absolutely insane. 1801? What? 1801? There wasn't even baseball in 1801. That's crazy. I did not realize it was that long ago. My gosh, why was I thinking 1860? I don't know. That's really nuts. That's really nuts. Because what's astonishing about that is that 100 years later, we finally figured out some other things about waves. I mean, there's other interpretations for this, of course. I mean, this could be due to constructive, destructive interference, but it could be due to other things as well. And I'll be honest, I'm not up on a lot of the history of physics like I would like to be. History of physics is awesome. One of the best classes I ever took in college was the history of mathematics. Ooh, that was such an amazing class. And it was crazy because I took that class the year that Andrew Wiles proved Fermat's last theorem. And we're like talking about it, and all of a sudden a paper comes out, and Andrew Wiles discovers solves Fermat's last theorem, and we're like, that was nuts. That was a pretty fun class. History of science, history of math, always excellent stuff. And it's a really nice thing to take those kind of classes because the historical perspective, understanding how humanity, has come to this knowledge. It's like a collective, it's not an individual. Well, actually, Andrew Wiles was one of those rare cases where it was if you don't know about Fermat's last theorem, Andrew Wiles kept himself in his house for something crazy like a decade. I mean, it was he was a researcher. He worked at a university, but he worked on this problem for years. I think it was like a decade, and then he solved it. And it's a theorem that was unproven for centuries. And the funny thing about it is, Fermat, he wrote, in the margins of a textbook, he stated the assertion. It was, x to the n plus y to the n equals z to the n. It has no integer solutions if n is 3 or greater. And he just kind of states it as it's a really simple proof, but I just can't fit it into the margins of this book I'm reading. So I'm just, but it's easy to prove. And then nobody proved it, and then Andrew Wiles proves it hundreds of years later with a proof that took hundreds of pages to do. So anyway, it was exciting. It was a fun time. Back to physics. Okay. All right, clear. Yeah, I did clear. All right, so remember these equations. When it comes to interference, you're going to see these quite a bit, actually. Quite a bit. So, question for you here. In Young's experiment, coherent lights pass through two slits. The term coherent simply refers to the fact that the waves are in phase. If they're not in phase, you don't get anything. You get a bunch of garbage. Because you need things to be in phase so that you have the path-like differences actually produce interference. Anyway, if the wavelength of light is increased, how does the pattern change? Put a letter in the chat there. Let me know what you think. B, huh? The bright areas move farther apart. I think I can buy that. I think I can believe that, right? Right. According to the equation, one side has a m lambda. If you up that, you automatically increase the d sine theta. You're not changing d, obviously, but the angles increase. So the bright areas do move farther apart. This is one of those circumstances where I really wish we were on campus, because the labs on this stuff are top-notch. They're very fun, but they involve high-powered lasers, which you're not really supposed to own if you're an individual. So it's not like I can say, hey, go buy these lasers and let's do some experiments. All right, in Young experiment, we have the double slit pattern here. What is the difference in distance between the +3 and the, wait, what is the difference between the distance from the S1? What? Oh, I see. Sorry. Yeah. So this is not worded in a. I don't like the wording of this. Anyway, what it's saying is that for the M equals 3 mode, what's the path length difference between source 1 and source 2? Yeah, this question needs to be reworded because there's no M for a single source. That doesn't make any sense. So sorry. The answer here is, 3, right. M equals 3 means 3 wavelength differences. Yeah, sorry, just to confirm here, it doesn't make sense to refer to M equals 3 for a single source. Well, at least in this chapter it doesn't. Hint, hint, wink, wink. Maybe next chapter that means something. Maybe. All right, a lot of questions here. Laboratory experiment produces a double slit interference pattern on the screen. Beautiful. If the screen is moved farther away, we're about to delve into that. We're going to move the screen farther away. What happens to the fringes? Oh my goodness, there's no fooling you people. There's no fooling you. Well, let me just make sure you understand what we're talking about here. You know, what you ultimately are getting out of this thing is you're getting a bunch of angles, right? Think about the tangent of these angles. The tangent of these angles is going to be given by y over L, where y is how far up or down you are from the central maximum, and L is your distance to the screen. Now, you're not changing your lambdas. That's set in stone. That's determined by the wavelength and the slit spacing. But if you move the screen out, in order to maintain the same angle, you're going to have to increase your y values. No fooling you people. All right. I'll try to come up with some trick questions. All right. So let's do this first problem here. And double slit interference pattern is observed on a screen 1 meter behind two slits spaced 0.3 millimeters apart. This is what I'll talk about earlier here. This is over 3 orders of magnitude difference. You need something like that to really see the fringes because the wavelengths are tiny. 10 bright fringes span a distance of 1.7 centimeters. We want to know what the wavelength of light is. This is a little trickier than you might think, actually. A little trickier. Let's jump into the example here. Where is that? Right there. Okay. Now, the value, well, let's talk about this here. Let me think here. Okay, so there's a few things I'll need to illustrate here to properly communicate this. Let's go with some, I love the lavender. I'm going to go with the lavender. It's such a common. So we got our M lambda d sine theta. Now check this out. If the screen is a meter away and the slit spacing is less than a millimeter, then we are dealing with extremely small angles. And there's this lovely thing we have called the small angle approximation. When your angles are small, they could, we're talking about 10 degrees or less, and this is far under 10 degrees typically, then your sine function is almost identical to your tangent function. They're basically the same value. I mean, you can punch in your calculator. Choose any angle that's 10 degrees or less. Your sine function and your tangent are going to vary by maybe like 1,000th or 2,000ths of a decimal. It's very small. So if we change the sign to a tangent, we can specify the tangent as y over L. And that's what this relationship is right here that I have. It's m lambda d sine theta. I changed the theta. Okay, anyway, so that right-hand side becomes dy over L. Move the d over. And I'm solving for lambda here. Solve for lambda. Now, d, we have the slit space is 0.3 meters, right? Now, if 10 fringes span a distance of 1.7 centimeters, check this out. What is the value of m? It's not 10. It's not 10. If you have 10 fringes, because what does this mean? Let's go back here. Let me show you this picture here. Let me show you something. Let's go right back, way back here. Look at this. If I have, say, 3 fringes, I'm going to go from 0 up to 2. I have 3 fringes. M equals 0, m equals 1, m equals 2. That's 3 fringes, but it's m equals 2. Because you should think about these m's in a way as spacing, right? There's one space between 0 and 1 and one space between 0 and 2. 3 fringes means m equals 2. So 10 fringes would mean 9 spaces, and therefore the value of m is 9. That's a little tricky, but that's what we have going on here. M is 9. In fact, the way that we could properly, illustrate this is that we have like a delta m and a delta y. If the delta y is 1.7, then the delta m is 9. Put it that way, maybe. Anyway, solve for lambda. We have our slit spacing, 3 times 10 to the minus 4. I just put it as a full decimal there. We have our spacing, the y value. We got our order number. And we got, we need an L here, 1 meter. 570 nanometers. 570 nanometers. 570 nanometers would be like greenish yellow light, like yellowish. 550 is pretty straight up yellow. So 550 is delving a little into the orange, but that's what would be here. Okay. All right. An individual fringe though is spaced apart by about 2 millimeters. Okay. So we divide that by 9. That's how we get that. All right. Any questions about this one? It's pretty simple as far as the math is concerned, but you got to really think about what it means for m. All right. Let's keep going then. Let's just keep chugging along. How are we doing on time? Just blowing through time here. All right. What do we got? What do we got? All right. Well, it's an in-class activity. Let's go through this example here, and then we'll just keep going. We don't need to take a break this early. I wonder why I'm so... I don't know. All right, so we got our double slit experiment here. The slit distance is 0.2 millimeters. Screen is a meter away. The m equals 3 bright fringe is 9.14 millimeters from the central fringe. Oh, look at that. So that's a very straightforward thing. We're told the m equals 3 fringe. So we're told the order, right? We could say, 3 fringes up or something like that, but that, But if you said, the distance between 4 fringes is 9.49. Well, that would be like 0, 1, 2, 3. Okay, but we're actually told the order number here. So this is a lot easier to do. So this is really straightforward, right? It's the same problem pretty much. Solve for lambda. We get 6.33 nanometers, which is pretty good red light. 6.5, like 650 or so is red. This is red light. This is red. This is deep red light. This is like your laser, like the laser lights. That's 650 to 700. So this is a softer red. Softer red. Yeah. Fantastic. Okay, so we're just gonna keep going on here. I'm going to keep pushing on here. Question for you here. I'm going to step away for 30 seconds. And, all right, so what we're doing here is we have our double slit experiment. And we're going to change the wavelength of light. If you were not aware of this, green light is a shorter wavelength than red light. So what do you think's going on here? Green light's like the lower 500 nanometers or so. A's, huh? All right. No fooling you here. Got it. Lower wavelength, tighter fringes. Absolutely. All right. Similar question here. We got our double slit experiment. We're using red light. We're going to take the slits that are on that screen, and they may be very close together, but we're going to move them even closer together. What do you think that's going to do? Uh-oh. A, C, and B. I don't know about that. Okay, so what are we doing here? You didn't see that. You didn't see it. D sine theta m lambda. You're not changing m lambda, right? You're not changing that. That's your path length difference. But if you lower d, you're going to have to up theta in order for that relationship to still apply. So the answer is C. The answer is C here. Okay. So we're going to take like a sound example here, basically. And we're going to work out, because, you know, we're talking a bit about figuring out distances with respect to the interference patterns. And we have something like that here. So we have these two, they could be sound waves or whatever. Radio waves. It's probably radio waves, right? And we want to know where the places of constructive interference are. And as we can see here, straight on a bisecting axis, we have constructive interference. Makes sense, right? Because path length difference is the same. We have an m equals 1 at 30-degree angles, and we have m equals 2 at 90-degree angles here. Okay. So that's the patterns there. And we want to figure out in what direction is the intensity from the two antenna the greatest, right? So let's do this problem. Okay, so we want to figure out wavelength though, right? We got to figure out wavelength because it won't, you know, we talk about wavelength in this stuff here. So these are radio waves. These are radio waves, right? And so we're going to use the speed of light because that's how fast they travel. And the frequency of the radio waves are 1.5 times 10 to the 6 hertz, and we get a wavelength of 200 meters. Now the same principle applies if it's light of any kind here. So we still have the same condition of constructive interference. D sine theta equals m lambda. What's d in this context? It's the distance between the sources, 400 meters. We have our lambda, and we want to find the different angles involved. Okay, so lambda was what, 200? The distance is 400. We end up with that the sine of theta are values of m over 2. Okay, now the way the sine function works is we can't have anything over 1. So we only have 3 modes here. We have the m equals 0, the m equals 1. Sine of negative 1 is 1/2. That's why we have 30 degrees here. We didn't know that ahead of time, obviously. And then m equals 2 is 90 degrees. And that's it. That's it. We don't have an m equals 3. Because an m equals 3 takes your sine function over 1. And that doesn't make any sense. So we only have 3 modes here. M1, M0, 1, and 2. Okay. We could try this for the minimum intensity as well. We'd have to use half integers. but these are the directions. Straight ahead, 30-degree angles, 90-degree angles. All right, great. Okay, so let's start with some applications, because that was pretty much, that's the physics behind the interference of light, at least for like the double slit experiment. So now we're going to do some applications of the stuff, and one of the applications that we can work on are what's called thin film interference. And this is something that is you can very typically see if you look at oil slicks. That's a good example of that. Sometimes when things are coated with a transparent material, for example, you might see this a lot on street signs because they coat street signs with a very thin transparent material. You can see this with eyeglasses too, unfortunately. You can see it with eyeglasses. And what you're seeing is this. When light becomes incident upon a surface with a thin film on it, like in the picture, this would be a film of oil. Oil would be in a lower density, sits on top of the water there and produces a very thin film. What happens is when the light becomes incident on the film, some of it reflects off the film. Great. But some of it will actually transfer into the film, experience refraction, change distance a little bit, hits some boundary underneath, say there's a boundary underneath, like this could be the water boundary down here, comes back up, hits the boundary between film and air, and then refracts and heads toward, the line of sight. Now, the ray that bounces off and the ray that refracts through will end up being parallel due to the laws of refraction. But guess what? The path of the one that went through the film is a slightly longer path. Guess what? If that path length is an integer multiple of the wavelength of light, you're going to have constructive interference. Okay, so when you see all the colors here, you know what you're seeing here? If you see reds, that means the film was of a thickness that had an integer number of red wavelength differences. And so the red becomes prominent. It's constructively interfered. If you see blue, that means the distance that a blue photon traveled in the film was a whole number of blue wavelengths. So the blue stands out. Okay, you might get a mixture of colors here. Well, 400, 700 nanometers doesn't have any multiples in it. So, I mean, you could, but I guess that would be very hard to do, I suppose. But anyway, so let's try to characterize this, because the physics behind this is pretty simple. The colors that you see are due to constructive interference. We know how constructive interference occurs. It occurs through path length differences. So we need to investigate the path length difference that occurs inside the film here. All right, fantastic. Let's do it. Let's just get to it. All right, now, there's a lot going on in this slide here. Quite a bit. Quite a bit. All right, first and foremost, we need to go back to, well, I mean, you saw this in the lab we did earlier today, and you saw this in, I think the lecture on Monday, actually, we covered this. When we talked about material waves, right? Material waves, when they encounter a boundary or they encounter a surface, when they reflect off of something, they can experience a phase shift or not, depending on if it's a fixed end or an open end. Well, it turns out that when light hits a boundary between two different indexes of refraction, we have phase changes that occur. Now, when light goes from a higher index of refraction to a lower index of refraction, there is no phase change that occurs. It's like having an open end. When you go from lower to higher, like say air to the film, then you have a half cycle phase shift. It's like when an incident wave hits the wall and then it's reflected and then you see that 180 phase shift there. Okay, so this is true for light, and it has what it has to do with. It has to do with the indexes of refraction. So high to low, no phase shift. Low to high is a phase shift. Now that's going to change, right, our interference equations. Because if you have a 180 phase shift, then constructive interference is going to occur at half wavelengths now because of the 180 phase shift, right? Destructive interference is now taking place at the integer wavelengths because of the 180 phase shift. So here's how it looks. Now, we got two sets of equations here. They look identical because they are. So now, to tell you what here, this requires you to very carefully walk problems here. It's a lot to keep in mind. Okay. Now, if the two beams of light experience a relative phase shift, that means one of them experienced a phase shift and said the other one did not, okay, then our constructive interference is going to follow the same patterns that we know. 2t lambda, m lambda, and 2t. For the destructive, it's going to be the half integers here. Okay, so that is when there's no relative phase shift. That's what we expect to see. And that makes sense, right? No relative phase shift. Well, the path length difference is just going to be a multiple of that. But if we do experience a phase shift, then the equations have to switch. If there is a relative phase shift. Now I say relative phase shift because either one can go through the phase shift. Depending on what the boundaries are, you need to work out what each ray of light, the one that reflects off, the one that refracts through, you got to really consider what's happening at every single boundary. And then in the problem, you say, okay, do I have a relative phase shift or not? Because it's possible that both rays of light both experience a phase shift. But guess what that means? No relative phase shift, right? And a relative phase shift, if you do have one, it could be one or the other experiences that. So this is tricky. It's a lot to keep track of. Be very careful when you do these problems. We'll obviously do a lot of examples right now so you can parse through this stuff. All right, let's just get right into an example here. Calculate the minimum thickness of an oil slick on water that appears blue when illuminated by white light perpendicular to its surface. Now, white light, if you didn't know, is a mixture of all colors. So we'll take blue light to be 470, and the oil's index refraction is going to be 140. All right, let's jump into it. Now, I want to make one statement back here that I got to communicate to you here. Okay. Where's that? So there are a couple things you got to take note of here. Now, the path length difference. Now, if you see these equations here, let's look at these equations again. What are we calling the path length difference? We're calling the path length difference 2t. That's the path length difference, 2t. T is the thickness of the oil slick. When you look at this and say, well, first of all, where's the 2 come from? Well, the 2 comes from the fact that you go down, you come back up. So you're going through t twice. But then the other issue is you're saying, well, there are angles here. Right? Aren't there angles? Don't you have to work out the actual length? It's not just the thickness of the film here. Well, guess what? Thin film. Thin film. When your film is sufficiently thin, there isn't a major difference between the actual path of the light that is at a diagonal and the thickness of the film. Those differences are so minor, they can be ignored. Well, at least for the purposes of what we're doing in Physics 211. You're trying to design something where you need to be very precise. Well, it's not a lot of effort to work out the triangles here. But tell you what, we have enough to worry about with the other physics. Trying to work out all the little triangle geometry is going to give you a headache. And I'm not about to give you a headache right now. Okay. All right. Oh, the other thing, too. Here's a really tricky thing. Say red light hits the surface between the air and the film, right? Goes into the film, comes out. You remember what happens to light when it goes through the film? When it goes through a different index of refraction, the wavelength changes, right? The wavelength changes. So if it's red light coming in, the stuff that's coming through here, in order to figure out the path length difference, is not the wavelength of the light that came in. You got to figure out what the new wavelength is based on the index of refraction. There's a million things to think about these problems. Let's just do the example, because right now your head's probably spinning. Let's make it slow down a little bit. Not going to promise it's going to stop, but all right. Calculate the minimum thickness of an oil slick on water that appears blue when illuminated by a white light perpendicular surface. Okay, so first thing to consider, let me zoom in a little bit here. First thing to consider here, what are my boundaries? What are my boundaries? We're going to hit the oil slick. It's a higher index of refraction. There's a phase shift. Right, I'll circle it. There's a phase shift happening right here. Now, then we go into the oil, and then we hit off the water and come back up. Now, what's the oil-water boundary? Well, you're going from higher to lower. No phase shift there. So we have determined now that we do have a relative phase shift. The top phase shifts, the bottom does not. There's a relative phase shift. So our constructive interference relationship has the half integer wavelengths in it. Uh-oh. What did I do? So 2t equals m plus 1/2 times lambda. We want the minimum thickness. That will be m of 0. Anything higher than m of 0 means a longer path length, which is not a minimum, right? And then your lambda is not 470. It's 470 divided by n. Because it's not blue light when it's in the oil. It's infrared. Ultraviolet light. It's ultraviolet light. Whatever 470 divided by 1.4 is. Ultraviolet light in there. So, solving for T yields 83.9 nanometers. So, in the setup here, a film that's about 84 nanometers should look blue. Because the blue light is going to stand out. Right? Blue light's going to stand out. Because that's what the two beams are going to be, your blue light. All right, so we're going to do a similar problem, but the initial conditions are just a wee difference. All right, so this is the same problem, except the oil is on glass, not on water, which means on the air to oil boundary, we still have our phase shift. And at the oil to glass boundary, we also have a phase shift. That means there is no relative phase shift. Both waves are half cycle shifted. There is no relative phase shift. So the constructive interference equation is the same as what we've been doing. So I put the same numbers through. Don't forget to change your wavelength. Very easy. I've been doing this for 20 years and I still forget to do it. Still forget. This one needs to be a bit thicker, right? Twice as thick, actually, right? 168 nanometers is the separation there. All right. And that would produce, if it's glass, right? Okay. Easy stuff. It's not easy. I mean, it's kind of easy. Easier. I'll put it that way. Easier. All right. Question for you here. Question for you here. An air wedge. We've got a wedge of air here. Separates two glass plates as shown. We have a wavelength that strikes. It goes through the glass. There are two reflections, one from the glass air boundary, and the other one is from the air to glass boundary. So the path difference is the little pocket of air that's here. Okay? So, given that circumstance, where are you going to see the bright fringe? Where are you going to see a bright fringe? So think about it. You got to think about the phase differences. Okay, let's think about the phase shifting. You're going from glass to air, higher to lower, no phase shift. Higher to lower, no phase shift. Air to glass, phase shift. You have a relative phase shift here. Because you have a relative phase shift, right? You got to have your half integer stuff. So lambda over 4 works. 3 lambda over 4 works. 5 lambda over 4 works. Okay, but the lambda over 2 and the lambda doesn't work. Okay, remember the thickness is 2t. Right, so it's not just whole wavelengths. It could be half wavelengths actually, because you got that 2 there. So 3/4. Well, 3/4 lambda over 4 works. In fact, look at the way this is set up. This is at an angle here, right? So there's a lot of thicknesses that could potentially work here. I might have a question related to that coming up. Oh, look at this. Apparently I do. Crazy. Let's look into it. All right, so we got the same setup here. We know what's going on. We have a relative phase shift. So here's our conditions for constructive and destructive interference. And what we're asked here is to determine what the spacing of interference fringes are going to be, right? Because what happens here is, because of this wedge and the fact that the thickness varies as you move along horizontally, then there's going to be patterns. There's going to be fringes there due to the different path length differences that are there. So the tricky thing about this is figuring out a function for T. It's not a single thickness. It's a variable thickness, so we have to figure out some kind of function for that. So what we're going to do is we're going to establish a proportion based on similar triangles. In the first proportion, I'm doing a ratio of horizontal distance to vertical distance, x over t. And I compare that to the full extent of the wedge here, L over h. Solving for t yields xh over L. X is my variable. Those are different distances from the far left side, which is the point of contact. Hi, Scout. All right. So I can substitute that in for t. What do I want? I want dark fringes or bright fringes? What is the spacing of interference fringes? Well, it doesn't matter if they're bright or dark, right? But I'm asked at the fringe at the line of contact, is it bright or dark? Well, is the fringe at the line of contact, this spot right down on the far left here, that would be a thickness of 0. So a thickness of 0 would correspond to a destructive interference thing there. So at the very edge here, you got a dark fringe. Well, no, I mean, I say dark fringe, but you don't see anything, right? So let's keep working with the dark fringes then. Uh-oh. We'll substitute in our value for t, solve for x, and we get 1.25 m. That's not meters, that's the order. That's in millimeters, okay? This is in units of millimeters. That's what I did here. So your wavelength is 5 nanometers, 10 to the minus 9, right? The distance is 1/10 of a meter in L. Okay, got my H in there. Okay, so both dark and bright fringes are spaced apart by 1.25 millimeters. If I plug in an M of 0, I get a dark fringe right there. The bright fringe is going to be exactly half of this value, right? So 0.625 millimeters is where the first bright fringe is going to be. In fact, if that's my space in 1.25 millimeters, I can divide the full distance, which is 100 millimeters, by this value here, and we get 80. So you're going to see 80 fringes. So if you look on the glass, you'll see 80 lines across. All right, cool. Very cool. All right, so next example. So I think I just have a ton of examples coming up. Let me just double check my slides and make sure I'm... Uh-oh. I made Zoom angry. Awesome. Great on time. We're going to be a little early. This is crazy because this lecture, when we're in class, takes forever to do. I don't know why it takes so long. But anyway, I almost never get done when I'm in class. All right, let's just jump to the next example here. This is fun. I'm loving this. This is when the class gets really fun. I mean, I love thermo. I love thermo. It's so much fun. I love thermo. I like all this stuff. What am I talking about? But this is really fun. I like the modern physics stuff. All right, so we got the same problem, but somebody was a little bit of a dum-dum, and they dropped this thing in water. So now we no longer have air here, but we have water. Well, you know, actually, here's the thing about thermo. I like it a lot. The only problem with it, though, is that we just really kind of scratched the surface of it. There's a lot of depth in thermo. And what's really fun about thermo is when you dig a little bit deeper, you start to get into the more micro aspects of things, the micro world. And then it starts to delve into statistical mechanics, cold physics, solid state physics. Then it gets a little wild. And then if you're really interested, you start to get into some material science. And I mean, for me personally, I love that because I like reading about quantum computing. I like to see the advances in solid state drives. I mean, I want those solid state I want a 10 terabyte solid state drive to be affordable. I got a 0.5 terabyte right now, and I'm not liking my 0.5 terabyte solid state drive. Although I did buy that years ago, though. Dude, SSDs? I can't believe they still sell hard drives like the old school. You know what's funny? I was actually at my computer yesterday, and I'm sitting there, and all of a sudden I hear this noise. I'm like, what is that noise? Sounds like a little... Like, what is that noise? Like, what the hell's going on here? And I realized that I actually still have a hard drive, a mechanical drive, when I built my computer, and I barely ever use it, but occasionally I have some backups in there, and I happened to actually edit a file on there, and then I heard the hard drive. I was like, oh, nostalgia for listening to the spins and the little tick, 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 ticks. I was like, I need a new computer. Last computer I built was 10 years ago. It still works, though. Well, everything, you know what's funny? The computers advance, but they're still the same darn money. I bought my system I put my system together 10 years ago. I built it for StarCraft 2 back in 2010. Yeah, I think I built 2010. And it's got an old i7 in there. I still upgrade the graphics cards. They still work good, even though I don't have the PC. I don't have the PCI 3 slot. I got a PCI 2 slot. Anyway, I can go on forever. I love computer building. It's fun, but I haven't done one in like a long time. But my old computer, 10 years ago, 1,600. Another computer, still gonna cost 1,600. Although I just bought a VR set, and it works good with my old computer. My 10-year-old computer, the VR set works. Anyway, sorry, going on and on about computers. All right, so so this is the same problem, except we have a different situation with we have a water boundary now. So did I have glass before? I think I did. There's still. Hold on here. I don't know why I have. I don't know why I need to be. Sorry, I don't know why I'm telling you what the index of refraction is in this example, other than you need to know for water, but you know what water is. Anyway, same as the last one, except now that we are in the space here, water is in the space here. Now we got to change the wavelength, right? So make sure you substitute your lambda with lambda naught over n. So you need to incorporate the index refraction, but the phase shifting doesn't change, right? That's not going to change. The glass to water boundary is still no phase shift, and the water to glass is a phase shift. So we have a relative phase shift here. You're doing the same stuff. You just got to put in a different value for lambda. And if we do that, though, let's go back to that example. We're driving the value of lambda down, right? So let's look at that. If we drive the value of lambda down, then the value of x is going to decrease, which means you can fit more fringes in the same length, right? And yeah, now our space is not 1.25 now it's 0.94, and now we can fit 106 fringes in there. Pretty nice. This stuff's awesome. Love this stuff. All right, so I got glasses on. When I bought these glasses, you know what they tried to sell me? Anti-reflective coating. Did I get it? Can you see? Did I get it? Nope. I didn't buy the anti-reflective coating. I probably should have, though. I don't notice a difference, but whatever. Anyway, it's a thing. Anti-reflective coating. And guess why they make anti-reflective coating? You joke. Oh, you know what? Is that because of, is it a Prime deal? Oh. I'll look that up tonight. Yeah, it's Prime Day. Even though Prime Day is 2 days. That's crazy. Really? A 5 terabyte drive is? I don't know. I'll look it up on Honey. I got the Honey extension. Tells me about the price changes. But anyway, yeah, thanks for letting me know. I don't know what you do with 5 terabytes, actually. I mean, I'm surviving. I'm surviving with my half. Or whatever. It's fine. This is annoying. All right, anyway. Lens coating. Magnesium fluoride is what they use. It's transparent. It's similar index of refraction to water. Dude, you know what's funny? You know, all the YouTubers are like, use honey. And I'm like, okay, whatever, I'll try it. It does work pretty good. The best thing about honey, honestly, is it saves you money on some sites, but they have a price tracker on Amazon. And they have a whole history. You can see if the price is lower than normal, higher than normal. They'll give you notifications, something like that. It's kind of cool. It's kind of cool, actually. I like that. I really like the price tracking, but I'm sure other sites do it, but it's just, you know, it's so easy. Don't call me right now, people. All right, anyway. So the index of refraction of the magnesium fluoride is 1.38. The purpose of this, though, is the non-reflective coating. The idea behind this is that it produces destructive interference. That's how it attempts to eliminate the reflective aspect that is difficult. There's a lot of ways to do it. We dabbled with polarization earlier in this class, and a lot of it's polarization. A lot of it's that way. Hold on here. One of my instructor friends is harassing me. 20 minutes. All right. So what we want to know here is what thickness does the non-reflective coating need to have for 550 nanometer light? Okay. If it's applied to a glass, glasses would have an indirect fraction of 1.52. So again, we're trying to establish destructive interference here. Okay. So what happens is the light comes through, some of the light's reflected off, some of it gets through, there's a boundary there. So that's the idea behind this. So we have air, we have our magnesium fluoride, we have our glass. You go from 1 to 1.38 to 1.52. That means phase shift at the air to magnesium fluoride boundary, phase shift at the magnesium fluoride boundary to glass, therefore no relative phase shift. Therefore, our destructive interference condition is the half integer multiples of lambda. Don't forget to put your lambda in terms of what it is inside the magnesium fluoride. We're not trying to cancel out the 550 nanometers, because when it gets into the magnesium fluoride, it's different. Solve for T, we get a 100 nanometer thickness. So a 100 nanometer thickness will eliminate the 550 nanometer light, which is pretty standard light. That's sort of the peak in a way of sunlight. Of course, there's other issues too. You can get polarizing filters that really helps with surfaces and things like that. Anyway,